talking about.
I know they're not related right now, okay?
Okay, draw this circuit. We're going to work through this. We're going to keep it pretty simple with easy numbers here. I want to find out how much voltage is dropped across each resistor and how much current is going through each resistor in this circuit.
It's the same as the source voltage.
That would be a very quick and completely incorrect response.
It says the voltage drops across each branch will be the same as the source voltage.
We'll add it up.
In what kind of circuit?
Parallel.
This doesn't look exactly like the circuit that we... So in a simple parallel,
Oh, I
yes.
didn't see the ones on the side.
Yeah, the ones on top make it a bit more
You
complicated.
are an evil, evil man.
This kind of circuit requires you to put the series circuit stuff along with the parallel. Indeed. To tackle a problem like this, as Justin suggested, we have to get it down to sort of a basic look at it so we can say, all right, we already know the voltage in the circuit. We have to find the total resistance first. But what we're going to end up doing in order to solve that is simplify this to one equivalent resistor. Find that current, and then we have to work our way back outward, making each step a little more complex until we get to this to find out how much current goes through each resistor and how much voltage is dropped across each resistor. But that is the first task. So we're going to find, so let's just put that down, find total resistance. We have to do this fairly... it's by the book, so I'm trying to think of the word. I don't know. It's not important. Not really efficiently. It's going to be a long process. A problem like this might take you a whole page. A good part of that will be drawing the circuits. So in order to solve this, we're going to start by combining any resistors that we can into one. Always start as far away from the battery as you can when doing this. And look at this last resistor. We can either combine these resistors, we can combine two or more resistors that are in series. We can combine those pretty easily into one equivalent resistor. Or if they're in parallel, we can combine them into one resistor. And we look, if we start on the right and start moving our way back, the next resistor in line, how do you describe these two? Those are in parallel, because the current would branch and either go through this one or that one. So these two are in parallel. So we're going to use our parallel circuit rule and resistance rule that we learned yesterday to make one equivalent resistor and just replace it in our drawing with that. So I'll show you what the drawing will look like as we do that. We'll still have our battery. Still have a resistor there and here. Still have the next one across the top. But now instead of these two branches, we're going to replace that with an equivalent resistor that is just across one branch. So this one becomes a bit simpler than the last one. So we still have a 10 ohm here, 10 ohm, 10 ohm. This will be something different that we're going to find out now by adding these two and figuring out what the parallel circuit with these two resistors in it looks like. And that will be the value for this resistor. And then we can move on to the next step. So let's do that. If we're going to add those last two that are in parallel, how can we find out their equivalent resistance? Add the reciprocals. So we get 1 over R, and since we've got R5 there, I'll call it R6, is equal to the sum of these two reciprocals. So 1 over 10 ohms plus 1 over 10 ohms. What's that? So it's 2 over 10.
Troy, what was that? 0.2.
Which it is 0.2, but then we have to flip that over. So it's easier if I just simplify this. That's 1 over 5 ohms.
So it's 5 ohms.
R6 then becomes 5 ohms, right, when I flip this back.
Just too weird.
Notice that what was our rule for parallel resistances if we look at the total?
It's always less than the smallest.
Always less than the smallest branch. And look, if they're the same, it ends up being exactly half. Because half of the electrons would go through this, half would go through this. They'd be equal amounts. They have the same voltage across them, so they'd have equal amounts of currents, double the normal amount of current, which means half the resistance. So this is a 5 ohm resistor, is equivalent to a 5 ohm resistor having those two 10 ohms in parallel. Yes, ma'am?
Where do you get the 1 over 5 ohms?
I simplified 2 over 10 is the same as 1 over 5. Okay, now we've got this one, our R6 I called it. That's why we got to practice. Yes, Chris.
So now, can you add those other two parallel ones?
Okay, which ones? So I've got,
The middle two.
I had R1, R2, R3.
R2 and R6.
Well,
Can't.
if R3 wasn't there, then you could.
Yes. Tom?
How do you know when you compare, like, two together?
That's what we're kind of getting to, why we can't do R2 and R6, because R3 is closer.
So R3 and R6, you
These two are easy. How are these two wired to each other? Series, one right after the other. So any electron going from here around this would have to go through both. That one's pretty easy to do. So if I redraw this equivalent circuit, I would start with my battery, have my R1, my R2, but now this branch I can make an equivalent that is these two put together. I'll call it R7. How much would that be then if they're in series? Series, you just add them up, right? So it's 15 ohms. We still have R1 here of 10 ohms, R2 of 10 ohms. Now you can do the parallel. Yes, Tom?
Can you go to the top circuit just for a sec? Okay,
So we're going from the right and we're just working
when
back
you
towards the
add together,
left.
You just get rid of N1. That's what
Right. Yeah, we're replacing, and we're going to keep it relatively simple. You know, this is already complex, but not much more complex than this, really. So you're not going to have to take 2 or 3 or 4 or 5. You know, you can prove that you know it just by doing a couple at a time. Yes, ma'am.
Wouldn't it end up to be 5 ohms if it was 1 over 5 ohms?
Well, this is 1 over the resistance is equal to 1 over 5. We wanted the resistance, so you have to flip both of those.
So why did we do 1 over the resistance?
Because that's the formula.
What's
The one that you wrote down yesterday. 1 over the resistance is equal to 1 over R1 plus 1 over R2 plus 1 over however many you have. But then you have to flip it back over. Okay, so now, as Carissa said, now we can add R2 and 7, they're in parallel. And so what we'll end up with is we'll combine those two into a circuit that looks like this. I'll go back up in a second.
6.
And that would be R8, our new one.
Negative resistance.
R1 is still our 10 ohms. We haven't gotten to that yet. But when we add these two in parallel, now we're looking for R8. We've got 1 over 10 ohms plus 1 over 15 ohms. Thank you. I'm going to write it out just so we can see. So these would go to 30. So 3 over 30 ohms plus 2 over 30 ohms equals 5 over 30. So that's not 8.5. R8 should be 30 over 5, which is 6. Right?
Yes.
Yep.
I think I put this as 10 volts up the top. And again, it's perfectly okay to use your calculator. I picked numbers that are working out easily with the fractional forms. Yeah,
Does 2 over 10 turn into 3 over 30?
I don't see a 2 over 10.
2 over 25.
I don't see a 2 over 25 either.
There's
1 over 10 plus 1 over
I got common denominators. Common denominator between 10 and 15 is 30. So this is equivalent to 3 over 30. That's equivalent to 2 over 30. Yes?
So when adding the parallel circuits, then the top other resistor doesn't affect it at all?
There's no units on it, if that's what you mean.
I mean, like, when you're adding like R2 and R7, what, does R1 have no effect on it?
No effect yet. We're building back to it. So we're just taking the easiest groups that we can and add them together, because our next step is now going to get R1 in the thing.
Do you have added like R4 and R3?
Where?
R4 and R3 because they're in the same.
We can't yet because that still has this one dangling out. So we have to start from the right and work back. So these two are the first ones that we have to add together.
So as long
There
as-
are more other methods that are a little quicker, but they're not as straightforward.
So as long as like there's no series in between the parallels.
Right, right. If the two closest ones are in parallel, you have to add them in parallel. If they're in series, then you have to add them. We've got just one left, which is pretty easy. Series ones we add. So we have our 10 volt battery. These two, since they're in series, are going to be 16 ohms total. I'll label that R9. So that whole big circuit at the top, as far as the battery is concerned, really just looks like as the same as a single 16 ohm resistor. It can't tell any difference between the 4 or 5 resistors we had at the top and one that's 16 ohm. But that lets us work with it. So I'm going to see if I can do a trick here and shrink this up a little bit so we can work all the way back up.
No shrinking. No shrinking. Be sure I get it.
Let me do what I want, whatever.
I don't know if I can shrink it just I want to shrink it just one to make it skinnier right to left, and I know if I can't do that. Okay. So, are we good with how we simplified this? I mean, certainly I can see where it would take some practice still. Any question?
This is the best thing ever, compared to everything else.
Yes.
This is what?
This is the best.
Okay, I was going to. I didn't hear what you said. I said this isn't harder than special relativity. Okay,
Put a lot of this on.
This is actually
Okay.
harder for me.
We'll get there. So I'm going to delete some of this part, so that, because now I want, if I were on a piece of paper, I'd try and limit this to the left 2/3, because I'm going to use the right 1/3 and go back up. I don't really have that luxury here, so I'm just going to delete the red. Because now I want to go back up and answer the rest of the questions, namely, what is the voltage drop and resistance across, or and current through each part of this. So let's start with this. Right? This is now as simple of a circuit as we can make it. I know that since there's 10 volts in the source, there will be 10 volts dropped across this, which is really those two. I can also figure out how much current goes through them. So let's do that first. So the current through my resistor 9 would be equal to the voltage divided by resistance. Yeah?
I have a question.
Yes?
What is current?
Current is the amount of charge flowing through a point or a circuit. So it's essentially how many electrons are going through, but it's measured in amps, coulombs per second. So by knowing Ohm's law, E equals I times R, we know the voltage, we know the resistance, so the relationship allows us to find out that. And that's going to go up, and we're going to be able to find everything else from this, since we simplified this. So that's going to be our voltage over the total resistance now, which is 10 volts over 16 ohms. It's going to be 6 point something, 0.6. 2?
Or 6. Yes, 0.625.
What units?
Amps.
Yeah, Tom?
Where'd you get R9?
It's going to be the current going through resistor 9. I'm just going to keep the numbering with that so we can see where each one is. Because there's no real resistor 9.
So resistor total.
Resistor total is number 9, is what I called it. Yep. Total resistance is 16 ohms. And I'm just adding one to each one, because as we go up, there's going to be a resistance and a current for each part, and that will help us keep it straight. So that's how much current is coming out of our battery. I'll label it I9. Now, as that goes through, it's actually being divided up amongst all the rest of the resistors, and going back up is going to show us how. Our next one up there, our simplified version, is still a series circuit. What can we tell about the current in a series circuit? It's the same throughout. And we know how much is coming out of this battery. We just figured it out. So that means throughout this circuit, the current, which will be for R1, and for this equivalent resistor 8, must be the same as is coming out of the battery. Okay, so that's one. We can answer now how much current is going through resistor 1 already.
So you're saying that if it's a series circuit, then all the resistors
Right.
have the same
And
current?
and let's say, so this is our equivalent, so we know that 0.625 amps is coming out of there. I'm going to jump way up to the top. I'll come right back. But if we know 0.625 amps is coming out of our battery, it has to go through this. There are no branches before it. So I can label that after finding that out. Yes, Tom?
So, what are you trying to find in the long run right now?
Every single, how much current and how much voltage is on every single resistor in our first one.
Alright.
So we're working back up from the simplified.
Can you scroll back down
Yeah.
to the second, that one? Why would it be the 10 ohm resistor, not the 6?
Both of them get the same current.
Oh,
Yep. Because it is the same everywhere. So everywhere in that, and now this is just a simplified version of the next one up. But we can use that. So we've got the current. That will allow us to find the voltage too. Voltage drop across each one. So what we found is that both of those would have the same amount of current, so we can find voltage pretty easily. We can find V1, which will be the current through this resistor times its resistance. So V1 is just 10 times that, or 6.25 volts.
And really, couldn't you just take 10 minus 6.25?
Yep. Either way you want to do it, you're going to get the same number. We know, since this is a series circuit, these two voltage drops have to add up to how much is there. So that would work. It should be 3.75. Let's multiply them out just to make sure. It's a little bit of rounding error, probably, but...
I get exactly 3.75.
Okay. So it'll be the current, oops, this would be 8 now. Going through our equivalent times R8. And that's 6 ohms. So you did get 3.75?
Yes.
Okay, so we can answer for, and we know everything we need to about the very first resistor then. We know how much current's going through it. We know how much voltage is dropped again across it.
Let's go. Troy wants to go back to special limited.
This takes practice. It takes you doing it a couple times, but there are 1 or 2 homework problems like this.
So if you ever say anything not done here.
Hey, how are my teams doing? I heard Eastern Washington put up a fight but lost in the first round.
You're out.
Harvard's out too, huh?
Yeah,
I haven't. I heard that the next day. I'm like, psh.
Am I still in? I have no idea.
UCLA, yeah, you have blue teams there.
You have UCLA. That's a pretty fight. That's a good one. Okay, so I'm going to put the 6.25 volts up here. Now, remember though, we know how much current's going through this R8, but R8 actually represents R2 and R7, which are in parallel. So what can we take from this? We know how much current's going through these two together, and we know how much voltage is dropped across those two. Those two are in parallel.
So the voltage is the same.
Voltage has to be the same because those two are in parallel. This right here is equivalent from here to here, which is both of those paths. But that means the voltage from here to here must be our 3.75 volts.
Which one is also like that?
What's that?
Which one else is 3.75?
These two, because they're in parallel with each other. So if one is 3.75, they both
So
are.
that means R1 is different, even though it's the same?
Same value of resistance, but a different voltage. It'll have a different current too.
So then the third one's the same thing too. On the end.
Sorry?
You have another resistor on the end. Like later on.
There's another resistor in between them too, though.
Oh.
Yeah.
So it goes down.
We'll discuss that at the very top, but we have to take step by step.
So R1 is 2.5.
So let's see. We've got R. Oh, sorry, that's a V. Okay, so now we know the voltage across resistor 2, we know the resistance, we can find the current. Do this one in green. So current of number 2 would be equal to its voltage over its resistance, 3.75 volts over 10 ohms, 0.375 amps. There are 2 ways we can proceed with the other. We can do the exact same thing with R7. So the current through that one is its voltage, 3.75 volts, over its resistance, 15 ohms. And we can divide that out. I also know that we had 0.625 amps coming, and then it split. So part of that would go through here, and we know how much that is. The rest would go through there. So we can just find the difference. Yeah, Krista? Oh, yeah.
So, what are all these I2s and V2s?
They're the I is current, V is voltage. They're the ones that go along with the resistor with the same number. We're trying to find V and I for each one, voltage and current for each.
So basically you work down and you work back up.
That's right.
It's like ladders.
You got to simplify, and then you can expand what you know. So the difference between these two is 1.5, it looks like. 2.5. 0.25. Thank you. Amps. Maybe there's a 0 in there. I can go up now and I can label how much I've got for voltage and current in resistor 2. Voltage, we said, was 3.75 volts. Current, 0.375 volts, or amps, sorry. Now I can move on to the next one.
So they're actually not the same.
They're not. They're the same resistor, but different values all the way through. And if these all three were in parallel without this one, we could say their voltages were all the same. But with that extra resistor in there, we can't. Yes, Matt?
Can we go back down again?
Of course, we're going back down because we need to keep working.
So, why did the amps change when you did the same thing?
Did the same thing here? These aren't the same things. That's a 15 and that's a 10.
Why did the change from 10 to
10, 15. We're talking about different resistors. That's why we have this 2 and the 7. So we have to put just the values that fit in there.
We're trying to find the voltage drops.
We already did that because they're in parallel. So they're the same. This R8 was equivalent to the two of them. We figured out it was 3.7 volts, 75 volts. And since these two are in parallel but equal to that, they each have the 3.75 volts. But they also share the 1.625 amps, which means some of that current goes through the first branch, some would go around towards the second. Okay, so now,
If both R2 and R7 are both 10 ohms, can we just divide the number in half and just do it that way? Down below?
yes,
Okay.
if they happen to be the same, yep. Okay, so now we know how much current is going through this part of the branch. R7, remember, was really these two. So it was 0.250 amps. So that means around these two, which are equivalent to R7, we have 0.250 amps. We also know that they share total the 3.75 volts that was across R7. How does that help us with those two? How? We need a, so how much, what can we tell because of this? Yeah, Kristen.
So can you use the current and the resistance to find volts?
Yes. We're almost skipping a step. I just want to make the point especially. Where is that current going? In this,
Through R3 and R6.
both of them, right? These two are in series, so if one of them has that much current, both of them do. So I think you had already jumped ahead to that. So that meant that this would be, the current through this one would be 0.25 amps, and the current through that one would be 0.250 amps. And then, yeah, then we're going to use, as you guys were suggesting, use those two use those two together to find the V. Yes.
So anything below that, the newly added section, you just
We are actually already figured these out.
just don't worry about.
Don't even worry about them anymore. We're just now taking the next step up and applying it.
Can you put B?
That's Greek for I.
So far my test, if I put that, it's okay.
It's okay. You're going to get ridiculed, and just like I am, though.
So then the current in a parallel, or no, what's the series circuit is the same throughout,
Correct.
but the voltage is
The voltage will be split up. Yep. So the electrons going through this portion all of them have to keep going the whole way, so the current is the same. But they'll lose a little different, they'll lose more energy in this 10 ohm resistor than in this 5 ohm resistor. And that's the voltage measurement. And we can find that now very easily by using Ohm's law.
Yeah, that's what I said.
Because we know the R and the I. So let's do that. So V3 would equal the current times its resistance. So the voltage drop across that is just going to be 2.5 volts. We can do it two ways. We know that they share this 3.75 volts, so I can predict pretty easily that it's going to be 1.25, or I can multiply it out. The current through that section times its resistance of 5 ohms, and we get the same value. R3 was one of our originals, so we can go back up and make a note of that we know the current through it and the voltage drop across it.
Mr. Schlemko?
Yes.
The voltage for V6 is 1.25, not 0.25.
Yes.
Yeah.
You
You
off
just
by
put the
decimal.
decimal now.
Sure am.
Troy thought he was right.
Technically, he's just doing this.
Yep. 1.25 there. Thank you. So here's what I'll say about that, Tom. If you get something screwed up like this, I will totally understand.
Good.
I will still have to mark it wrong. But I will totally see how easy that is. And I will feel for you right in here.
So you don't only mark it off with a point.
But now I know.
Depends on how, if it's that kind of error and then that propagates, I'd mark this part wrong, but then the next part I would probably not. You should also be checking just to make sure that it makes sense, and I should have too. Okay, so now we have resistor 6 is actually these two. We know the amount of current going through resistor 6 was 0.250 amps, and we know the amount of voltage dropped was 1.25 volts. But really, resistor 6 was these two that are in parallel. So how do we use that information to go forward? What is that? Why is the current the same? You're actually, in this particular case, you're not wrong as long as you say it's the same as each other. But we can't in general say that about a parallel circuit. But what is the same?
Well, it doesn't matter if you take the first one or the second one because you're still going to have to take the same path back.
Okay, so what is it? Where are you getting at with that? You're right.
What is he asking?
So voltage will be the same. Because from here to here is the equivalent of R6. Those two paths, as Troy said, they're essentially the same. They go through a different resistor, but the voltage has to be measured the same. So we can actually say then V4 must be the same as the voltage that we found for R6, 1.25 volts. And so must 5. Okay, I'm going to erase this to give us a little more room since we've got it recorded. Okay, and now what? Now we got to find the current. Current in Ohm's law equal to voltage over resistance. Voltage here is 1.25 volts over 10 ohms. 0.125 amps. And as Mariah very astutely noticed, even before we had calculated, the current through the last one is the same because they're the same resistors. So if we did the calculation, it would be the same numbers in here, we just replaced these 5s. And we made it. This kind of analysis is useful in electronics because very often you will have different, this is called a voltage splitter. You might have one voltage source, like a computer has, well, they have 3 really, but they might have a 3 volt, a 5 volt, and a 12 volt line. Okay, well, I need 7. So you would start with your 12 volt line, and you'd have to split that up. And the way to do that is to have very different resistors here, so that if I took a measurement off of this, well, now I'd have 2.5 volts if I put something else out there. And so that's how you can kind of divvy up the voltage that you're allowed.
For the current of the first one, was it 6.25 or was it
0.625. Should have been. We can go back down and look. So that would be the 10 volts, 16 ohms. And also note that as we're going through now, we've got 6.25 volts out of the 10 here. That means the rest of this has to share the 3.75 volts that's left. Also, we've got 0.625 amps coming through, and that means this branch plus everything else must equal the 0.625, because part of it goes through here and part of it goes on. And this 0.375 plus the 0.25 that continues is the same. It's much more complex when we're looking at it like this. But if you take the steps and the time, it's actually, we don't have much work time left anymore. But it's a good example problem to do.
So that's why people hate parallel circuits?